Welcome back everyone to this new episode of our journey together exploring vision systems and more generally, imaging systems. Today, we continue analyzing our vision system diagram by taking a closer look at what we can consider the core of our system, the camera. The camera, in fact, is the device capable of converting light information into digital information, thus creating the actual image. The image will then be analyzed later to extract further information from it. So what is a camera made of? A camera is mainly composed of two elements, a sensor and control electronics. The sensor is the component that performs the initial conversion from light information, that is, from photons to an amount of charge. Then, the control electronics come into play, converting the amount of charge into digital information. The sensor, specifically, is made up of sub-elements called pixels, which are able to capture the photons contained in the light, and thus convert them into an electrical quantity. Exactly. If we want to use a hydraulic analogy, we can think of the pixel as a bucket that collects water, which in this case would be the light information, and gradually fills up. Once the bucket is full, the control electronics step in to empty it, and then convert all this water into digital information. There are two types of cameras, those called area scan cameras and those called line scan cameras. The first type has pixels arranged over an area, so along an actual matrix. The second type, on the other hand, has pixels arranged solely and exclusively along a single line. The first type is definitely more common, widely used, and also well known. The second type, on the other hand, even though they are less common, are still widely used in certain fields, especially in industrial settings, because they have the ability to achieve a very, very high acquisition speed, a very high frame rate, as it's called in the field. In this presentation, however, we will focus mainly on area scan cameras, primarily because, being more common, these cameras allow us to better understand how the process of transforming light information into digital information takes place. Area scan cameras, in turn, can be made up of two different types of sensors, CCD sensors or CMOS sensors. The main difference does not lie so much in the type of conversion from light information to electrical information, but rather in the second conversion from electrical information to digital information. So now let's take a detailed look at how CCD cameras work. In a CCD sensor, the conversion from charge quantity to digital information takes place through two processes, a parallel process and a serial process. First, a parallel process moves the charge row by row toward a new element called the shift register. At this point, a serial process comes into play, gradually emptying the charges that have reached the shift register. These two processes are repeated gradually until all the charges inside the pixels are emptied. And so the actual digital image is formed. Once the pixels are emptied, they are refilled to form a new image. But electronically, how does this conversion actually happen? In a first mode called interline transfer, the sensor is divided into two areas. An active area, where the actual conversion from light information to electrical information takes place, and another area called the buffer, where the charge is transferred to then be analyzed with the two processes we saw earlier, parallel and serial. A second mode is instead called frame transfer. In this mode, the two areas, the active one and the buffer, are not arranged column by column, but are placed exactly one above the other. In this way, the transfer of the charge from the active area to the buffer happens all at once, and is then converted into the final digital information, file. So thanks to these two processes, it is actually possible to convert light information into a true digital image. Unfortunately, the CCD sensor suffers from some issues, particularly problems of blooming and smearing. Blooming occurs when the intensity of charge contained within each individual pixel is somehow sensed by the adjacent pixels as well, creating a sort of halo in the final image. Smearing, on the other hand, happens due to the vertical dragging of charge quantities, where sometimes pieces of charge are lost and remain in the adjacent pixels. This creates a sort of vertical line within the final images. In these two images, we can see both blooming and smearing effects happening at the same time. In fact, we can see that there are both halos and vertical streaks that actually don't exist in the real scene. Despite these issues, the CCD sensor is still a high-quality sensor that allows for very high image resolutions, though this comes at a high price as well. The sensor is very well suited for applications where the brightness is very low, such as, for example, an astronomical application. Now that we've seen and understood how the conversion works inside a CCD sensor, let's take a look at how the same conversion works inside a CMOS sensor. The CMOS sensor differs from the previous one, again in the stage where electrical information is converted into digital information. In this type of sensor, in fact, the conversion of the amount of charge happens all at once, because inside each pixel there is a small analog to digital converter that actually performs the real conversion. This type of sensor is very good, offering very high resolutions and also high frame rates, so extremely fast acquisition speeds. One drawback of this sensor, however, is the extreme digitization of its pixels. In fact, unlike in CCDs, the pixels do not communicate with adjacent pixels, but only with themselves. So let's say they're not exactly social pixels. So to sum up, let's look at the main differences between these types of sensors. The CCD sensor generally offers good resolution and excellent image quality, but it also has higher energy consumption, higher prices, and overall more complex electronics. Image acquisition is usually slower since, as we saw earlier, the transfer occurs via a shift register. And there are also several possible unwanted optical effects such as blooming and smearing. However, the CCD sensor usually works very well in low-light environments, as we have seen. On the other hand, with the CMOS sensor, it is possible to achieve faster acquisitions and lower costs. Additionally, this sensor offers good resolution and good image quality. For these reasons, it's very well suited for mass-market applications. In this lesson, we therefore focused on the main part of our vision system, the camera itself. We learned how it works. How does the process of transforming light information into digital information take place? And so at this point, we have a real image available to us. This image, as we'll see in the next lessons, will then be further processed to extract useful information from it.